This is Lesson 9A, Unit 11. We're going to be calculating pH for weak acid with strong base before the equivalence point. So I have a little drawing here of what we're going to be doing. We have pH, mLs of sodium hydroxide, and we're going to be looking at 3 points. The initial, right about here, then we're going to look at the half equivalence point, and so that will be our three titration calculations that we'll do. So let's start with our first one. We're going to calculate the pH before we've added anything. In other words, 0 mLs of titrant right here. So we have only 0.10 molar HNO2, so we're just going to set up an ICE table, and we have 0.10 molar. Water is not part of the equilibrium, or not an important part that we have to worry about. We're going to start making our hydronium ion and our nitrite ion. We're losing nitrous acid. Our equilibrium concentration is 0.100 minus X, X for hydronium, and X for NO2. We are going to assume X is small, that X is going to be much less than 0.100 molar. And that's because 100 times 4 times 10 to the negative fourth is smaller. So we're going to have 4.0 times 10 to the negative fourth is approximately equal to x squared over 0.10. Remind ourselves that x is equal to our hydrogen ion concentration, and we calculate the value as 0.0063 molar, so our pH is equal to 2.20. Next, we're going to calculate the pH if 15 mLs of the 0.1 molar sodium hydroxide is added to 50 mLs of the 0.1 molar of the nitrous acid. So our total volume is 65. Our moles of sodium hydroxide that have been added so far is 15 times 0.1. We're going to use millimoles, so this is 1.5 millimole. So what we're doing is we've established that our initial pH was 2.20. Now we're going to be calculating at 15 mLs. All of our values here, we're going to use millimoles just because it's going to make life easier for us. 50 times 0.1 is 5 millimoles, 5.0. The hydroxide millimoles is 1.5. We don't care about the water. And initially we have none of the nitrite ion. The hydroxide is our limiting reagent, so we'll lose 1.5 minus 1.5. So we have 3.5 left afterwards of the nitrous acid, none of the sodium hydroxide left, and we have 1.5 millimoles of the nitrite. So notice here that now we have A minus and HA. We have a buffer system. So we can use that pH is equal to pKa plus log A minus over HA. Now our pKa is equal to the negative log of 4.0 times 10 to the negative fourth from the original problem, and that is equal to 3.40. So pH is equal to 3.40 plus log A minus over HA, 1.5, and this is millimoles, 3.5 millimoles, and our pH is equal to 3.03. Now I want you to take a look at the ratio of HNO2 and NO2 minus here. At this point we have that the concentration of HNO2 is greater than the concentration of NO2 minus. So let's amend our little chart that I have right here. This is called our half equivalence point here. That's where we're going next. What we have figured out at this point right here is that HA is greater than NO2 minus, right at this point right here. Okay, now we're going to look at the next step in the titration, and that is going to be calculating the pH of 25 mL of 0.1 molar sodium hydroxide added to 50 mL of 0.1 molar of the nitrous acid. Our total volume is 75 mL. Our total moles of sodium hydroxide is 2.5, so that's 25 mL, 0.1 molar, and let me go, this is millimoles, so let's write that out, millimoles. So what I want you to do is to complete this BCA table here. So you're going to complete the BCA table, so pause the recording and complete it. Alright, you should have completed the BCA table, and you had 5 millimoles of the HNO2, 2.5 millimoles of the hydroxide. You end up with 2.5 millimoles of both the weak acid and its conjugate base. So we have a special case here where not only have we made a buffer system, so we have a buffer system here, but we also have what is called the half equivalence point, where the amount of HNO2 is equal to the NO2 minus. So this is a special case at the half equivalence point, and you should be familiar with this term. So I'm going to underline it. So this is the half equivalence point. At this point, the concentration of HNO2 is equal to the concentration of NO2 minus, which means when we substitute in to pH equals pKa plus log A minus over HA, that we have a 1-to-1 ratio. So we have that 3.40 plus log 2.5 over 2.5 is going to be 3.40. This was our initial pKa value that we established from the Ka value on the previous page. So we had already calculated the 3.40. So notice this is a 1-to-1 ratio, and every time you take the log of 1, it is equal to 0. So at this point, our pH is equal to our pKa. So at the half equivalence point, pH is equal to pKa. This is a technique that we can use to determine the pKa of a weak acid. We go to the half equivalence point, shown right here, and at this point pH is equal to pKa.